These first couple examples may be trivial, but we're trying to understand the idea of square root. So we know that anytime that we are repeated multiplying, we are applying a exponent. So because 5 times 5 is 5 squared and 25, we can say that 5 is the square root of 25 because it took 5 squared to get me 25. 5 is the square root. Let's keep going. This means 10 squared, which is 100. Therefore, 10 is the square root of 100. And we can keep this going. This is x squared. So x is the square root of x squared. This is where things get a little tricky. We know that we can add these x to the 6th. So what is the square root of x to the 6th? Well, this was x cubed squared. It was repeated 2 times. So then x cubed is the square root of x to the 6th, which means this is x to the 9th squared, which is x to the 18th. Whether you multiply these to get 18 or add these to get 18, we could say that x to the 9th is the square root of x to the 18. Now another thought experiment to go backwards to say, okay, what if I have the final answer and I want to know what did I multiply by itself to get that? So the question then becomes, what do I add to itself, or what do I square to get x to the 1st? And the answer is a half. 1/2 plus 1/2 is 1. 1/2 times 2 is 1. So 1/2, x to the 1/2 is the square root of x. So we're going to divide the exponent by 2, particularly when we have variables. On this next page, we have some vocab to go over. Whenever we're dealing with rational numbers, meaning fractions, it can be rewritten as a radical, meaning square root. Rational just means fraction. Radical means square root. So I can rewrite this. We need to understand something. The x is the base because it is the bottom of an exponent. The exponent is the numerator and the root is the denominator. So we know that this whole thing is kind of the exponent, but the basic exponent is the numerator and the root is the denominator. So we could rewrite this as the square root. The base stays in the bottom underneath. The exponent is the 1 and the root is the 2. Now these are invisible numbers. Most of the time we would just rewrite this as the square root of x. We all understand, we already know that raising to a 1 is trivial. We don't write that. We also do not need to write the 2 because as I read just this, it is the square root. So we read this as the square root, but we understand that square is a 2. There's an implied 2 here because it is the square root. So we understand now that this is the base, this is the simple exponent, this denominator is the root. So this is x raised to the 1st power and the square root. So x is the base, 1 is the power, and 2 is the root. Again, we don't need to write that. This is the base of x. The root is 3, and the power is 2. This is the base. This is the radical. The denominator is the root, and the 3 is the power. Now, I do want to point out there's 2 different ways that we could write this. We could write this as, this is in rational form. There are 2 radical forms that we could express this as. Both are going to have x as the base. Both are going to have the 2 as the root. However, the difference is this. In this case, I'm going to raise the entire thing to the first power. In this case, I'm going to raise the first power underneath. The only difference is the order of operations. This order of operations says do the inside first and then do the root. This says do the root first and then take the exponent. Again, this is a trivial example, but sometimes it's quite different. This is the way that makes sense to do if you don't have a calculator and you're trying to evaluate numbers. So in radical form, this root is also called the index, and the inside is called the radicand, the base, right? So the previous base was the radicand. This root denominator was the index. So in radical notation, x is the base, n is the index or radical, and m is the power, right? We know that the negative doesn't change. Well, what does the negative do? Let's think. It changes the location. So it means that my answer is occurring on the bottom. X is the base, the denominator is the root, and m is the power. And if there's nothing left, there's a 1 in the numerator. Notice how in this case, I put the m underneath the radical. In this case, I put the m kind of like after the radical, and they are equally the same. They're equally correct. So on the bottom here, let's just rewrite this in notes form. So for a, n, and m, if they're all numbers, integers, not letters, for a base of a raised to the n over m, excuse me, I think they wanted m over n, we can rewrite it as the base or radicand of a to the nth root m power. Or we could rewrite it as that. Depends what you want to do first. They are equally the same. So when you get something like this, my recommendation is to do it this way. Because as we know that roots in a tree go down, we want to be dealing with a smaller number, and powers go up. We don't want to be dealing with a large number. So the half exponent is weird. Whenever we think of something weird, we just want to change it to something we're more familiar with. We're going to change this to 16 to the second root raised 1. Now, I'm not taking my own advice. This 1 should be on the outside. In this case, it doesn't really matter. Do you know what the square root of 16 is? Well, it means what times itself. It's saying blank times blank equals 16. We know the answer is 4. So this is 4 to the 1 power, which is just 4. This is saying 27 is the radicand, 3 is the root or the index, and 1 is the power or exponent. Well, this is saying blank times blank times blank equals 27. And the answer here is 3. 3 to the 1 is 3. This is saying the cube root of -8 and then 1. Now I put the negative inside because the negative is being applied to the 1/3 is being applied to the negative as well because it's grouped together. Now here's a good question. Can I find a number when I multiply it 3 times, I get -8? Let's forget the signs first. If there's going to be a negative in the answer, there better be a negative in the question here. So is it true that a negative times a negative times a negative is a negative? And it is true, because if I multiply 2 negatives, I get a positive times this remaining negative, and this would give me the negative that I want. So I know that my answer is possible. Now that we figure out the signs, let's figure out the numbers. If I want to get an 8 repeated 3 times, it needs to be quite a small number. Let's try 2. 2 times 2 is 4, times 2 is 8. So the answer is -2. -2 to the first power is just -2. Now this is saying the fourth root of 16 and then raised to the first power. What times itself 4 times is 16. So again, if it's being multiplied 4 times, it better be a pretty small number to get 16. It turns out the answer is 2. 2 to the first power is 2. On the next page, I just want to point out that you are responsible for understanding certain perfect squares and certain perfect cubes. Why don't you pause now and write as many perfect squares and cubes as you know. So as far as numbers go, I would expect you to know as much as these. So something to note, if I want to find the square roots of 49, you may know it off the top of your head, or you can just count. Square root of 1, this is 1, this is 2, this is 3, 4, 5, 6. The seventh number is 49, so the square root of 49 is 7. Now notice that I went all the way up to 15. 15 squared is 225, so the square root of 225 is 15. Then I jumped up to 400. The square root of 400 is 20. It's the 2, and then another 0, 20. And then, 20 times 20 gives the 2 zeros there. Perfect cubes. Cube root of 1 is 1. Cube root of 8 is 2. Cube root of this is 3. And then 4. And then 5. As far as letters go, I want to point out that anytime we are squaring a thing, it's a perfect square. So if I square x, I get x squared. If I square x squared, I get x fourth. If I square x third, I get x sixth. If I square x fourth, I get x eighth. So you can see they're all even. Perfect cubes, x cubed, x6, x9. You can see that they're all factors of cubes, of thirds. All right, so this is the rule that we all know. These I think you could do on your own without a calculator. Again, my sincerest advice is to go down before you go up. Now what gets interesting is at the bottom here when we have multiple. We have both the power and the denominator, the index. So here it's critical that we take the square root of 100 and then cube it. Square root of 100 is 10. Square root of 100 is 10, and then I'm going to cube it to 1,000. Okay, the fourth root of 16, and then cubed. Well, 16, so it's not up at the top here, because I don't have perfect fourths. But you should be able to kind of think through this. What times itself 4 times? So my trick of the trade is 4 fingers out. I want to count 4 times, and I want to get to 16. So it turns out that 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 is the answer to that, and then cubed is going to be 8. And you can continue that.